Our goal is now to study vector analysis. Our approach to vector analysis will be via differential forms. So, you must be wondering, why differential forms? Before I motivate the study of differential forms, let me recall for you 3 theorems from classical vector analysis that you should have studied when you took an elementary course in multivariable calculus. These 3 theorems are extensively used in both physics as well as engineering. In particular, if you have ever taken a course in electromagnetism, you would have applied this result a number of times to derive Maxwell's equations. So let me state these 3 results. The most familiar one would probably be this theorem, p dx integral over a closed curve p dx plus q dy is double integral over, I'm not going to tell you what exactly the double integral is over. I will speak about that in a moment. Del q by del x minus del p by del y dx dy. Okay, so this theorem is known as Green's theorem. Not only is this theorem very useful in physics and engineering, one can use this theorem to give a very elegant proof of the famous Cauchy's theorem in complex analysis. Now, let me describe the notation a bit more. This is supposed to denote a line integral on a closed loop, and this double integral is supposed to be the double integral on the region determined by this closed loop, the interior region determined by this closed loop. It will take me a little bit of time to explain what this interior region is, so I will postpone it as this is just a motivational lecture. Now the first question that springs to mind is, what is this meaning of p dx plus q dy? In an elementary course in vector analysis, what usually happens is this is just defined in an ad hoc manner, and this result is proved usually just for rectangles or triangles or some simple figure. Without explaining really what this object means, you just define this whole thing, what this integral is supposed to be. It's supposed to be the line integral. Okay, so this was Green's theorem. The second theorem which I am going to state is the divergence theorem. That this is triple integral of divergence of a vector field. F is a vector field here, is nothing but double integral of that vector field dot the normal vector, and this is taken across a surface. So this is a surface integral. So the left hand side is a volume integral, the right hand side is a surface integral, and this surface is in question where you're integrating over is nothing but the boundary of this region on which you're taking a triple integral. Of course, I'm intentionally being a bit vague and quick so that I can get to the heart of the matter quickly. I just want to state these 3 theorems so that we are all on the same page. So this is the divergence theorem. This is the divergence theorem. This is Gauss's divergence theorem. And the third result that you would have studied in classical vector analysis is the one involving a curl, the curl of a vector field. This says that the line integral of a vector field with respect to arc length is nothing but the double integral of the curl of f dot the normal vector, and this side this is a surface integral. So this notation that I'm using, ds on both sides, shouldn't really confuse you. It's just some sort of convention that is common. So this is an integral that involves the curl of a vector field, which gives another vector field that is dotted with the normal vector. So since I'm not going to be using caps and dots in this course, so caps and hats, let me just remove this hat for convenience. Okay, so this result is known as Stokes theorem. Stokes theorem. Okay, so to really distinguish the s's on both sides, maybe I should make this little bit bigger s, so that it's sort of clear that it's a surface integral. Let me just do that in a different color. Okay, so these three results you would have seen, not maybe exactly in this form, but in quite a similar form. These are the three classical results from vector calculus. And as I mentioned in a beginning course on multivariable calculus, these results are usually proved for a special case or a heuristic physical argument given as to why these results are true in general. But a proof of this is usually not done in an undergraduate basic course in multivariable calculus, simply because the classical proofs of these three theorems are quite long and tedious. Now this puts us in a difficult situation, because when a mathematician sees a nice, simple, elegant, intuitive, physical, heuristic argument for these results, but at the same time the rigorous proofs are long, tedious, computational and devoid of insight, then there is a tension. Why is it that the easy argument is not giving us an easy proof? So the way the mathematicians have solved this issue, this tension between the physical arguments that are easy and the mathematically precise classical arguments which are long and tedious, is to shift off all the tediousness to the framework. So essentially what we are going to do is we are going to develop an elaborate framework of differential forms. Once you do that, of course this framework is going to be tedious, boring, dry, but that's unavoidable. Once you develop this framework, all these three results can be subsumed by one result called the general Stokes theorem on a manifold. Not only can you subsume it in one Stokes theorem for a manifold, it will turn out that that single Stokes theorem proof is not at all hard. Of course, it is still a bit of computation is involved, but it is not at all hard. It is not long. You can do it in 2 pages. So the net result is all the difficulty has been moved to the framework. Once you master that framework, the results that you're really interested in have very simple and elegant proofs. So you might ask, what is the merit in moving everything to the framework instead of having all the tediousness in the proofs? Well, the reason is the framework has to be learnt only once, and once you learn this framework, it becomes a really powerful language. For instance, all the laws of electromagnetism can be expressed using differential forms in just one equation. So the basic idea is that you master the framework, and once you master the framework, everything else becomes easy. So that is the reason why there is merit in this framework. So my suggestion to you when you watch these videos on multilinear algebra and differential forms, which are the framework part, don't get bogged down by the details. Watch it once, then read the notes where all the proofs are given in detail. Read the proofs once, then watch the videos again and be done with it. Many of the proofs will never be used later on. The essential key points will be the results about differential forms, the existence of a wedge product. The wedge product is sort of the generalization of the cross product that you have seen in elementary vector algebra. So once you see the proofs worked out in detail, then it's not really a good idea to remember all the tedious proofs. What is essential is some basic properties of differential forms and the wedge product that you need to remember. Once you know that, the rest of this set of videos will become rather easy, and you will appreciate the elegance and beauty of this framework of differential forms and multilinear algebra. As an additional bonus, we will do some elementary things with tensors. In case you decide to pursue a course in physics in the future on relativity, this will prove to be extremely beneficial, because tensors and differential forms also happen to be the framework of Riemannian geometry, and this is sort of the language of modern general relativity. So this learning this framework once is not This framework is not just single focused on differential forms used to prove Green's theorem and Stokes' theorem. It has many much uses outside electromagnetism also. It is used extensively in general relativity. So your efforts will pay dividends. So this is some motivation as to why you must study differential forms. So all the best in your study. This is a course on real analysis and you have just watched the video Why Differential Forms.